All right, so we're gonna get back to the quantum computing simulator. Tomorrow, Advent of Code starts, and so I'm hoping to start my series tomorrow on Advent of Code. If you don't know what that is, it's adventofcode.com. I think it's a coding challenge for the first 25 days of September that a lot of people do, and it's super fun. And so I want to stream that. I'm not going to do it exactly on time for two reasons. One is I don't stream every day, and some of the problems, especially the later ones, are probably too intense to do in the 2 hours that I usually stream. So, and also I have plans for some of those times. It is the holidays for part of it, but then the last thing, and maybe the biggest thing, is you're explicitly sort of forbidden from streaming it until the competitive part is over. So there's like a leaderboard and stuff, and if the leaderboard is still open, then I can't stream it. So I imagine I'll end up starting it tomorrow, unless the leaderboard doesn't fill up very quickly, and then going from there, and I'll probably end up lagging a little bit and finishing it, towards the end of December, early January. But should be fun. I'm excited about it. They're really cool problems, and it's fun because kind of feels like the whole world is doing it at the same time, which is really neat. But today I wanted to kind of wrap up the quantum computing segment, and originally my goal had been to get to the kind of Shor's algorithm and the order finding algorithm, which is the quantum part of Shor's algorithm for factoring large numbers. And kind of as I've been doing this, it's become clear that it's certainly achievable, but I'm not sure it's actually the most interesting thing, in the sense that if I visualize, can I even visualize this? Let's see here. Let's comment this out. In the sense that if I try to Fourier transform, is it quantum circuit, Fourier transform, 4 qubits, let input be quantum register basis 3 or something. So if I visualize this, which is a much simpler circuit, it's a quantum Fourier transform, it's part of Shor's algorithm. Well, it's part of the order finding subroutine, which is part of Shor's algorithm. What I get looks like this, which is a bunch of matrices operating on vectors of complex numbers. It looks pretty cool. You can see at the end that the result is this cool rainbow thing. It's pretty cool to see, and it helps my getting to this point helped my intuition about how quantum computing works tremendously. The order finding algorithm, which again is part of Shor's algorithm, it's the quantum part of Shor's algorithm, operates on 2 to the 2 times 2 to the n qubits, where n is a little bigger than the number of qubits it takes to represent the number you care about. So very quickly, even in super simple cases, 15 is 3 times 5. You want to factor 15, it takes 16, it takes 2 to the 16 qubits or something, which is not going to visualize well. Be really cool if it did. I do think there's an interesting bit of artwork that you could create by doing this with a more powerful graphics engine than Nano, and it'd be super cool to see it all rendered there. But I'm not sure it's going to teach me very much. I'm not sure it's going to teach you very much. It's certainly not going to render quickly. It's certainly going to take a bunch more time to like optimize and switch out the visualizations and all that. And it doesn't quite have the properties that I wanted the final goal to have. So instead, what I want to do today to kind of wrap this up is improve the visualization, to have a little bit of UI in it, so that it's easier to kind of explore what quantum circuits do and how they work. So I only have 2 hours today. I'm going to basically just try and add a handful of features that I think would be nice to have. So let's think about what those features might be. So first off, I'm going to change one of the goals here to just be simulate the quantum Fourier transform and inverse quantum Fourier transform. And then visualize quantum circuits in order to help explain what's going on, provide some UI for playing with those circuits. And in particular, what do I think would be a good set of UI tools? By the way, I can get rid of a bunch of this. And these are fine. So let's see, UI. So I would like to be able to choose an input basis vector. I would like to be able to choose the number of qubits of our circuit. I would like to CRUD, create, remove, update, create, read, update, delete. Is that what it is? No, create, update, delete. Create, update, delete. Gates. I think those are the main things. And ideally, optional, hover over square to get complex number. I think that's actually like a little annoying to implement, so I might not do it, but we'll see. But I think certainly the first two are doable during this, and we'll see about the third one. So let's look. So. All right, so what we're going to do is, I think we just have a default state. I think when you type a number, it should update the number of qubits and the circuit, ideally. I'm trying to avoid buttons. Let's start with that. Let's start with you type a number and it updates the basis vector. So let's say up, down, alt. Let's fix n qubits first at 4. Let's make this and whoops, n qubits, and this the 0 basis vector as a default. And then, and I guess I'll just get rid of these. And then it'll just do the Fourier transform for right now. But if we get a key that is like 1 through 6 or something, we'll update key number, key digit, num, numpads, let's virtual key code. Sure, let's do numpad 1, and let's say model.input model.input model.circuit is basis. Oh, can't be numpad 0, it has to be numpad 1. Numpad 1 is 1. Fourier transform basis 1. Let's actually do this differently. Let's do this as for each key. I want to consume keys down. Key numpad 0 or numpad 1. This doesn't even work that well. I should think about this more carefully. So basically, we want to let's set how many qubits first. So if we want to set how many qubits, then we need to basically re-instantiate. So let's create an instantiation function. Instantiate. And this will be pub function model zoomed drawer. Wait, maybe model just is the instantiation. Let's say update n qubits, and let's say model at mute model n qubits usize and we recreate the thing, and then this becomes alright, I guess this is fine. I guess we could impl model here and say say that all this stuff is good. Not sure I really need all of this. And then this update function can be a method then. And this can be itself. These become self. As does this. And then this can be, whoops, this can be model new, window, zoomed drawer, new app.draw. Circuit input. And something like this. Okay, and then we just, when we update, we need a way to update the number of qubits. I really want to use the number keys. So what is this? Winit event key code, virtual key code. So let's see what that is. Winit event virtual key code. It's key 1, key 2, key 3, and so on. Yeah, okay. So we can say key 1 model.update and qubits and so on. 6 is about the max. And now cargo run this. 3. Hee hee. Oh, that's actually pretty slick. That makes me happy. It's a little one qubit quantum circuit there. And if I say 5, does it get prohibitively slow? It gets quite slow. I wonder if I can reuse these rectangles somehow and make it a lot faster. Should think about that. Okay, and so then maybe we can use the numpad to be basis vectors, or we can use plus or minus. Plus and minus seems kind of good. Let's do that. Key plus will be model update basis vector and what to say about this? You know what we can do is we can say call this input basis, and then key minus, and we can update the model to not keep around a quantum register. Or do we need a quantum register in there? We can do it during drawing, right? Yeah, we can do it during drawing. So we'll have the input basis be just a just U32. So U32 here. 32. And actually, let's have this be self.input basis. What's up? Oh, it needs to be a U size. Fine. Okay. And then what's going on here? Oops. And self input basis. That's not okay apparently. Oh, input basis is now just so I guess we can just not do that anymore. And input we don't do this anymore. We just go 0. We'll do update input basis, we'll say. count in a moment. And then somewhere in here, the register will be, we'll just say let input register be a new input basis. New basis. And then it's n qubit. So these are reversed. N qubits is just n qubits, I think. Yes. And then this becomes register. And input register. And this becomes the register. And now we just need to implement the new function. Probably update input basis. Let's input basis. Call this input basis. And cool. Let's see what happens. So now if I do, I can change the numbers, and if I say plus, nothing happens. Tend to subtract with overflow, sure. That's logical, okay. So we need to clamp this, basically. Let's see here, if model.input basis is greater than 0, then we do this. Wrong one. No, sorry, if model.basis is less than model.n qubits, model.circuit n qubits minus 1. Then we do that. And actually we'll do it out here. Take all this. And oops. This. Nice. And then same thing here. If model.input basis is greater than 0, then we do this. Should keep it from subtracting with overflow. But it's not really changing anything. Why not? Whoop. So if that input basis equals input basis, that looks right. Input, and then in the view, we set the input register to the input basis. And we draw the register, and we use that to compute all of the other registers. So why would that not work? During the update loop, not really doing anything. Oh. No. The input basis. I mean, we saw it overflowed, so if it's going to overflow, that kind of means that it's getting updated. Basis, self input basis. Register is the result, which starts out as the input register. Interesting. And we don't use the input basis anywhere else. Draw gate, draw basis, and qubits, index, coefficients. So draw register says we need to get the coefficient from the register, but that's fine because input register is the basis with input basis. Slightly confused. Doesn't matter if I hit shift, doesn't matter which plus and which minus I use. Okay. Well, do we have draw text somewhere? We can just do it with the draw, right? Let's just draw. What if I just say model.drawer.text? Yeah, that. That's the color. Text takes a color and an XY. Color white. How do I do colors normally? Color RGB2. Okay, this is fine. Color RGB U32 text color. And where's that going? Sure. It's just for debugging purposes. Input base is 0, it says, no matter what I do. Very interesting. Very, very interesting. Need self. Self input basis equals input basis. Model. Model doesn't run every time, right? Model runs. Update runs every time. Model only runs at the beginning. If model.input basis is less than it, and I put push plus, it should get updated. Not greater than 0, so this should never happen, but this one should happen. Just to check, let's make these map to P and Q for the moment. I'm not using those, make sure I'm getting my key strokes right. P, oh, Q. Okay, cool. So something is wrong with my notion of what the plus key is. It's a little weird. Also, it occurs to me, this should be 2 to the n qubits. 2, shit, what did I do? Color RGB 32 text color, and then this should be 2 U size power this -1 as u says, as u32. And then something weird about the plus and the minus. Something weird. Something weird, and I don't know what it is. Virtual code plus. It is not documented. That's helpful. Is equals documented? Yes. So it really seems like shift plus should be the plus sign. I wonder if I need shift and plus. I wonder if I say equals and minus if it works. Does. And minus works. And if I press shift, it doesn't matter. Okay, I can live with that. I can live with that. And now we can go look at what the outputs look like. And it'd be nice to be able to scroll a little faster, but what are you gonna do? And we can get some pretty cool colors from our quantum Fourier transform. Okay. I think I might just call it here. And say this is an okay stopping point for the quantum computing simulator, and then go and do an archived advent of code question, because they're fun and I'm stoked about it. So let's do that. Let's just merge this.